It is a common misconception that once you leave the atmosphere, gravity disappears. This side-by-side chart compares Earth's surface gravity to the pull experienced in orbit. Down here on the ground, we feel 100% of Earth's gravity, but at the altitude of the International Space Station, about 250 miles up, that pull only drops to 90%. The gravitational force up there is almost as strong as it is right here. So if the Earth is still pulling on them with massive force, why do astronauts look like they are floating inside a weightless bubble? To solve this trick of orbital mechanics, we have to look backward at the earliest mathematicians who tried to decode the sky. Johannes Kepler was one of the first to find a pattern. He realized that planets don't move in perfect circles, but in predictable, stretched-out shapes called ellipses. He proved that the cosmos follows strict mathematical rules. But the central question remained: how can a massive object physically pull on something else across millions of miles of empty space? Isaac Newton found the answer when he realized that the force causing an apple to drop from a branch is the exact same force holding the moon in the sky. This animated diagram visualizes Newton's universal law of gravitation. He calculated that gravity's strength is dictated by the mass of two objects and the distance between them, represented here by the equation F equals g times mass 1 and mass 2, divided by the distance squared. Now, watch the glowing line connecting the spheres. If you double the distance between the two objects, the gravitational pull doesn't cut in half, it drops to a quarter of its original strength. This steep drop-off is known as the inverse square law. Newton mapped the mechanics of the universe, but his equation had a blind spot. That letter G, the universal gravitational constant, represented a number so microscopic that the instruments of his era couldn't actually measure it. It took another 71 years for Henry Cavendish to finally calculate G using a highly sensitive torsion balance. With that tiny number, he successfully weighed the Earth, discovering that our planet hides an incredibly dense, heavy iron core beneath its crust. With G solved, Newton's equation proved that gravity has an infinite range. Every atom in the universe pulls on every other atom, acting as the ultimate cosmic glue. We can use Newton's mechanical logic to solve the modern mystery of the floating astronauts. They are experiencing a physical state called constant freefall. The sensation of weightlessness happens because the astronauts and the station itself are plummeting toward the Earth at the exact same speed. This diagram shows why they never crash. The inward arrow represents the downward pull of gravity, but the horizontal arrow represents tangential velocity. The ISS is moving forward at an incredible 17,500 miles per hour. As the ship combines extreme forward speed with a constant downward drop, its trajectory perfectly matches the curvature of the Earth beneath it. Orbiting a planet means falling sideways so incredibly fast that you continuously miss the ground forever. Newton's laws were masterpieces of prediction, but they relied on a force that seemed to act instantly across a total vacuum, a concept that even Newton found difficult to explain. In 1915, Albert Einstein provided the missing mechanism. He realized that space and time are not empty containers, but a physical fabric. Massive objects warp this fabric, creating steep, funnel-like curves that dictate how everything else moves. Through this lens, the International Space Station isn't being tugged on by an invisible string. It simply rolls along the natural, curved path Earth's immense mass carved into the surrounding space. By treating gravity as geometry rather than a simple tether, Einstein provided a map accounting for the relationship between motion, space, and the flow of time. Because massive objects warp the fabric of space, they also warp time. This creates gravitational time dilation, where clocks tick slower the closer you get to a heavy mass. This requires constant mathematical correction. If our GPS satellites didn't adjust for this slight time warp in orbit, the navigational maps on your phone would fail every single day. On a galactic scale, massive gravity wells anchor entire systems of stars. At the center of the Milky Way sits Sagittarius A star, a supermassive black hole with a gravitational pull so immense it binds our entire galaxy together. Yet, when astronomers observe how fast these galaxies spin, the visible matter isn't enough to hold them intact. The math dictates there must be dark matter, an invisible substance responsible for 85% of the universe's gravity, keeping fast-spinning galaxies from flying apart. When the most massive objects in space violently collide, they send physical ripples outward. These are gravitational waves. By the time these waves pass through Earth, they stretch and squeeze our planet by less than the width of a single atom. Gravity acts as our primary sensory tool, allowing us to build instruments sensitive enough to detect these microscopic ripples and map the invisible forces shaping the cosmos. Down on the human scale, our bodies evolved to rely on Earth's downward pull. It acts as a physical trainer. Without it, astronauts lose bone density and muscle mass, so they use resistance treadmills to simulate weight in orbit. We also use planetary gravity to explore outward. By flying spacecraft close to massive planets, we steal a fraction of their orbital energy, using their gravity as a slingshot to boost probes like Voyager across the dark voids of the solar system. Gravity dictates how a clock ticks, the structural strength of our bones, and the sweeping arcs of galaxies. It binds the rhythm of our daily lives on Earth to the infinite spinning dance of the stars.